Here are some example solutions from the lab extension. Let's say our Lego bot moved 20 centimeters per second. So in all three cases, the velocity is 20 centimeters per second. Now let's do a prediction just for this first motion right here. For number one, I'll make my sketch, and there's my object at time equals 0. I know that it's going to move the whole time with a velocity equal to 20 centimeters per second, and it's going to be somewhere at 9 seconds, which is given, and the position at that point I don't know. That's what we want to predict. That's the position at time t, and the position initially is given as 38 centimeters. So this is a sketch that goes along with this given information. The graph I would sketch would be position versus time, and it would look like this. This is just a rough draft of a graph that is rather rough, but it's what I know. I know that I have this starting position at time equals 0. At 9 seconds, I don't know what the position is. I could use this graph to get the answer with some brute force. Every 1 second, I know that I have a 20 centimeter change in position. So over 1 second up 20, over 1 second up 20, over 1 second up 20. I could do that 9 times and come up with an answer for that. Or I can use the equation to do this. I'm looking at a straight line, so I'm thinking y equals mx plus b, but I see I don't have y, I have x for position. My slope is the average velocity. I don't have x, I have t for time, and my y-intercept is actually my initial velocity. And I want to know x when time is 9 seconds, so the 20 centimeters per second is the velocity, and that's a constant. And multiply that times 9 seconds and add to it the 38 centimeters, and that is equal to the position at 9 seconds. And 20 times 9 is 180. I can see the seconds cancels out. I get 180 centimeters plus 38 centimeters, and that would be 218 centimeters is the position. When is it the position? When time equals 9 seconds. Groups that had a chance were able to test their predictions, and this is a prediction with the actual robot, and the results were very good. There was no more than a few centimeters difference in any case. So someone, if they were off by 4 centimeters, might have said they went over. The difference between calculated and observed was just 4 centimeters. Let's take a look at number 3, which is a little different here. The information given is in this sketch. At time equals 0, it's position 0. At time equals, and then the motion is going to go on, and at some time the object is going to be at the 50 centimeter mark. We want to use our constant velocity particle model to figure that out. Here is a sketch of the graph for this situation. I know I'm going to get to the 50 centimeter mark starting from 0. I just don't know the time. So let's see. I'm not going to try to figure this out with the graph. Let's go to the equation. Trying to solve for t. It's going to be at the 50 centimeter mark. And I know the velocity is 20. I don't know the time. And it's starting from 0. So I'll just leave it like this. And I just need to solve for t. So if I do so, that's a multiplication, so I'll divide by 20 to isolate, and I'll have t equals, now I'm going to put the units back in, 50 centimeters divided by 20 centimeters per second, and what happens is the centimeters cancel out. I'm left with 1 over seconds in the denominator, which will become seconds if I simplify that, and this turns out to be 2.5 seconds. So if a bot that travels 20 centimeters per second travels for 2.5 seconds, it will go 50 centimeters.